You do, instead of doing one per period, you do 3 of them, so that it goes faster. So that it has less time to lose voltage. Yeah. So anyway, what that means for the problem is that we come up with this formula that you're basically just going to have to remember, because otherwise, because I don't know how to get it, but you're just going to have to remember this formula that the current from the induction motor is equal to radical 3 of the current that is given. So, and then you have to do the same thing for the voltage as well. And so you have to remember that VL equals radical 3 of V. You're never going to have a different phase. It's always going to be 3, or you're not going to have to remember this. But if you do have to remember this, it's radical 3. So we have these, and then we calculate IL, which is, this is given as 100. So 100 times radical 3. Have you guys memorized radical 3 like I did? 1.73. Yeah, 1.73. 100 times radical 3 is 173. Woo. Fun. And then you come down here, and we know voltage. Yes, we do. We know voltage is 2400 times radical 3. I don't think I actually did that. I did. Equals 4157. Did you just plug it in the calculator and get that? Beautiful.
Yeah, you're right.
Yeah?
I dropped
Decimal?
yes.
Okay. So we got 4157, and we did actually plug these numbers into the calculator. I'm not just making them up. And then what you do is you say P is P. I guess that must be S. I don't know. We use P. P equals ILVL cosine of theta is our formula. And the cosine of theta, if you remember from our triangle that's gone now, it's the power factor. So we know that in this case, no, it's not power factor. What do we do? Oh yes, okay. So this is the power factor of the motor, which is given as 100%. So this is 1. So, knowing that this is 1, we go through and we say 173 times 4157 gives you some outrageously large number, which is 720 something. 7200013. So outrageously large, and this is, I don't know why they didn't convert it to watts, but they didn't. So it's VA, which is volts times amps. Very complex, very weird. So then what we do is now we're trying to find power factor by definition of power factor, which is the amount of power that actually comes out versus the power that we use. So this is the power that was given to the system, and then the power that's used is this 500 horsepower. So what we do is we take this 500 horsepower, P equals 500 HP, and we convert that into watts, which is 1 horsepower equals 1 HP equals 746 watts, which we got from looking up on Google. Thank you, Google. And knowing that, then what you do is you take the power that's, actually, let's make this make sense. This should probably be S. Then it'll make sense, I think. Yeah, it will. Yeah, it will. Yeah. Trust me. So then we have our formula, PF equals P over S, right? Yes. So then we take this is the power, this is the all of it. And then so we have 500 times 746 over 72,0013, and times 100% if you're cool, which I think in this problem we're actually not cool, so we don't do that. You just take the decimal place, which is what? What'd you say? 5.18, which we round to 5.5152, because these are all multiple choice problems. So the one that is closest to 0.518 is 0.52, and thus we have victory! Woo! Let's write victory a little here, right? Units on power factor. Anybody? Everybody? Power factor units? Anybody? It's unitless. Exactly. Woohoo! Power factor, unitless, because it's watts over watts, which is cancels. Which is lots of fun. That stuff is gone. And now we can move on to the next problem. Thirteen. What size capacitor to make the power factor equal to 0.9? So we have this wonderful circuit. Very simple. No mistakes. Easy. No mistakes. I did books right now. It is 0.8. And okay, so plus I wrote it all down, so it's different. Okay, so the first thing we do is, let me make sure I did write it. You wrote some of this for me, didn't you? Or is this one that you worked on? We both do. No.
Which one is it?
You wrote this one down. Was I lazy?
Yeah.
Okay, I was just lazy. Okay, just making sure. Okay, so. Why hello, Tim. Welcome to tutoring. You missed the first problem. That sucks.
It was the most important.
It was the most important. We went over all the crazy things like power triangles. This is important, Tim. I'll go over it one more time. S, Q, P.
Oh. Yes, power.
Power triangles. Okay, so you have real, imaginary,
Imaginary.
P, Q, S. Theta cosine of theta equals PF. PF equals S. I can't do anything. Okay. P over S. Okay, you remember all this stuff, Tim?
Yeah.
Cool.
Yeah.
Kinda, yeah. We're using it later, so that's why I went over it again, very, very quickly. And that's what 15 minutes of the video, so is all that stuff. So kind of important, in my opinion. Kind of important. We do use it for the next 3 problems, or I do. Jeremy does weird things.
Phasers.
He does phasers. I do power triangles. Okay, so what we need to do is we have the reactive power causes the power factor. So we need to reduce the reactive power by including a capacitor into the circuit. Maybe this is sounding familiar to people, maybe not. So we're trying to counteract the power from the inductor and align the phases a little bit better to 0.9. And we do that with capacitors, if you guys remember. So I drew the power triangle, Jeremy drew the power triangle again. So we have P equals 50 kilowatts. Now it's straight.
Look at math workbook. Assume this is right angle.
15 degrees. Okay, so this is imaginary. You remember this is S. PF equals cosine of 0.8. I'm not going to write that down again, but I will write down S equals P over PF if you do magic. And so then what we do is we get S is equal to 50 kilowatts over 0.8. We're master mathematicians, so we know this is 58 point something. Okay, now that that's done, we can then go and we have Q over here, we have S. Okay, so now I know where I'm going. So what's going to happen is we have this beautiful power triangle, right? We have, let's do it like this.
50 over? I disagree with your number.
50 over 0.8?
60. Yeah, it should be like 63. 63.
It is 63. I just can't do, I can't read. No, I'm doing some of this from memory, so I'm not getting all my stuff from the, it's 60, we have 62 and a half, yeah. Okay, that's what happens when I read my papers, I get the right number. When I think about it, I maybe get the right number. Okay, so what we're doing is we have P, Q, S, and this is initial, this is our initial triangle, and this is our final triangle, S, Q, P. And so what we're doing is we know that the, huh?
Side to side.
You lost me. Okay, so we know that that when we add a capacitor into the circuit, it's an ideal capacitor, so the real power is not going to change at all. So we know that the real power over here is not going to change at all. So, and based on this formula over here, we calculated the S in the initial version. So what we're going to do is based on the new power factor, this is PF equals 0.8. This one's PF equals 0.9. So what we're trying to do in the new power factor is we're going to find, we found S here. So I believe we're going to find, actually we found Q next. So, yeah, so we're, oh yeah, okay, so
Use imaginary.
we're going to find, so after we found S, we're then going to find Q of this one. So then based on this Q, then we're going to use the ratio of the power factors and Q's to find this Q, and then determine how much Q goes into the, how much power goes into the capacitor. And then using that capacitor number, we will then find out what the size of the capacitor is. Is that making sense to folks? See where we're going? Maybe. We're going from one triangle to the next, and then going from the second triangle to the capacitor. Cool. Okay, awesome. With that in mind, we will erase the triangles, because now that we know where we're going, who needs diagrams? You guys all wrote it down anyway. And if not, then S, P, Q, how many times can you write that down before it's memorized? So we have Q, and we all call these primes for fun, I think. No, we didn't. That's a lie. That's a lie. Don't do that. Okay, we called the second one primes. So then we have this wonderful formula, Pythagorean theorem, except we're going to alter it a little bit, so we get Q equals the square root of S squared minus P squared. You guys all remember that, right?
37,500.
Yes. Is that what it is?
Yes.
I should actually check my numbers. It is. Except we have K. And if you remember, when it's reactive, it's VAR for some, I don't know why. I don't know why.
Is power reactive.
It's power reactive, so they have some funny reactive units, which is VAR. I mean, volt-amp reactive? Yeah. I mean, I don't know why it's not like RW or something, but reactive watts. I don't know. I didn't make it up. I just go with it. So the next thing we do is we say that S prime, which is our final, our corrected power complex, is equal to PF. That's not right. P over PF. Right? Somebody has that formula down. They can tell me that I'm right. Because I love to hear that I'm right. And then we are going to say that this is 50K, because we know it's the same, because capacitors add no real power. And then we're going to do the power factor, which is 0.9, and then we get 58. Here's my 58. No, that's still not my 58. I'm remembering something else. It's 55 point something. 0.5. We have 0.6. Yeah. Okay. So that's there, and I'm going to try to stop remembering faulty numbers. And then we do q prime again, and then we do q again, but you know this time it's q prime, and then we get.
What's S in? Is it also?
That's why I'm getting weird. Wait, what the heck? What am I doing?
S is in watts also. Right? Versus P. Really bad.
S is in VA,
Oh right. Okay. Hold on.
S is VA.
because you made the good point of watts are real,
Yeah.
and this is, S is the complex.
So what is real?
You're real.
It's real because you can convert it to probably what's the other use? Joules per
Yeah,
second. Probably joules per second is a watt.
yeah.
Joules per second.
What problem am I doing? 13. 14. 14. Okay, I'm just gonna trust these numbers, I guess. Okay, so this is 40 squared. And then it should equal 20. Are you sure this? 13? This is 50. That's why. Okay. I'm going crazy over here. Sorry. There we go. That's right?
Yes, I agree.
Yeah, okay. So now here we go. I was gonna write the right number, just squared, of course. 24.2? Yes, get that? Cool. Okay. So we're all still on the same page. Sorry, the next problem is like it's just weird. It's the same, it's almost the same numbers, so it's very confusing to me. Okay, so now we're almost there. So now we have q minus q prime. No, other direction. Q prime minus q equals
How are we gonna get
q capacitor. I mean, yeah, we are going to get a negative. You're right. That'll happen. But
13,000?
yeah, 13.3 actually. Let's do it this way. Okay. Anybody else need me to do that very simple calculation? Or are we good? Cool. Okay. I've done it really. So now we know the power through the capacitor, which is not what we're looking for. Or is it? No, we're not. We're looking for the actual capacitor, I think. No, why did we do that? We also didn't finish this problem, Jeremy. We're very mean. Why did we not finish this problem? Okay, so
Did we
what
stop
is
at
the overall system power factor is the question, so we don't need this stuff.
Wait, wrong question again.
We're doing 13. 13. Oh my gosh. 13. What size capacitor? Okay. Okay, that's why we stopped here. Okay, so we did finish the problem. I'm just going crazy because these problems look the same. They're measured in power, which is why we stop here. So now we know the power. So the only question left is, do we add this in series or do we add it in parallel?
Series.
We add it in series? I don't remember.
Yes.
We add it in series.
Why?
Because like what is it? What's the term? This is Z is impedance is
Yeah.
is like
Yes.
resistor kind of thing.
Yeah. So
It's resistor like.
so we're putting it in series, you said. Cool. Which is correct. Good job. Awesome. Now I'll pretend that didn't happen and I'll move on to 14, which is very much the same.
It was 13.2K.
13.3K.
Negative 13.3K.
Negative. Yes.
Except it is negative, but power is never negative, so.
So we just wanted the power across the oscillator.
Yes. Yes, we did.
Power, I thought we wanted the ohm or carrots or whatever.
You know, you would think so, but this problem, all the answers are in power, so we wanted the power. Got me. Now we're on the power factor. Okay, so we have this wonderful setup where we are now, yes. Okay, so I drew 3 triangles out here. I'm not going to draw them because you guys know triangles, but I drew the first one for, what? He wants the triangles. Okay, so I drew one for this, and one for the whole thing. And you can just trust me on that. And the notation that we're using is we have P, S, and Q, and this is R, and then we have P, S, and Q, and this is Z. Did we use Z?
That was probably fine.
We used L. Yes, we used L. Because it's ZL. Yeah. And then we used, you would think we'd use normal, but we actually used T.
For total.
For total. Yes. They're coming out of my head, so.
Rather than OS for overall system.
Okay. So, so what we know is that this is the resistor, this is the inductor-ish thingamajig, inductor resistive load. So what we know is that the conservation power, we know that the power through the whole thing is the power of the components. So we know that PR plus PL equals PT, and we know that's true for every variable, is that, yeah. So the first thing that and we know that for Q as well. So the first thing we do is we find S for, so we find S for the first one, which is,
0.
which is 0. We did not find this for the first one. We found S for the second one. Yeah, we found S for PL. I should really read my notes before I say things. PL over PF. There we go. It's a lowercase p for the first time. Equals SL, which SL equals PL is 40 over SL is, or not, PF is it given?
50K. Yes, it's 0.8.
0.8, yes. Cool, so we have 40 divided by 0.8, which is some number, 50K. 50, you know what makes 50 cool?
It says K.
4, 5, 3, 4, 5. QL equals 30K. It's a 3, 4, 5 triangle.
I see.
Yeah, 3, 4, 5 triangle gives us QL equals 30K. Yep, I think we actually did the math on that, and then we're like, oh cool, it's a 30K. But, so then we know that QL plus QR equals QT, which means that QT equals. Come on, you were the one who said 0, so finish it for me. Plus 30K? Yeah. Q. Can anybody read? I'm so far down. I'm gonna change that. Okay. And now we're on P's, which we said P plus P equals P. So P R equals 10. Actually, let's just do this. PR plus PL equals PT. 10 plus 50, 40 equals 50. Okay.
P's the bottom one, right?
Yes. P's
Oh, so
real.
Oh, so it's not necessary, okay.
P is real. Why? What's confusing?
I was gonna say it's not necessarily just an inductor. It may or may not have some other.
Well, it has to have some resistor of some kind to get 40 kilowatts of real power.
That's true.
Yeah. So we know that there's some kind of real thing in there.
We do.
Yes. So now that we know QL, we know PL, you know where this is going. Triangle. PL squared plus QL squared. PT squared equals plus QL squared. QT squared equals ST squared. Dylan, welcome. You missed quite a while, but that's okay because we're videotaping.
Yeah, that's yeah.
Yes. So, the next thing. So, Dylan, the important thing, everybody probably knows this by now. We have triangle I, R, imaginary, real, P, Q, S, real power, reactive power, complex power, theta, cosine of theta equals PF, the power factor. Therefore, PF equals P over S. That stuff literally using for like the first 4 problems, 3 problems, however many problems we use it for.
Okay.
So, that stuff important. If you have any questions about it, you can ask me or wait for the video. Where was I? This part. So we have 50K squared plus 30K squared equals ST squared. Anybody want to do the math on that? Or I can look. 58. Finally. Finally, with the 58, it finally shows up. All right, so now we know that ST equals our original. What was our original goal? What is the system power factor? Which is
P over S.
P over S. And we know those things.
So his reason is
P over S equals 50 over 58, which equals
857.
0.857, except that this is multiple choice, so we know it's 0.86.
That is not.
Okay. All right, cool. Any questions on this problem? No. Awesome. Sweet. Hmm?
I don't see enough triangles.
No, I was lazy. Dylan, just for the record, we used 3 power triangles in this question. Yeah. The power triangles, PQS, PQS, all the subscript R, PQ, they're all PSQ. PQS with subscript L and PQS with subscript T. So it's all fine. I'll actually leave that problem up for a little while for fun. Except you got this, so I can erase it.
Yeah. What was S, P, and Q again?
Complex power,
Okay.
reactive power,
Okay.
real power.
Got it.
So P is the power through a resistor, Q is the power through an inductor or a capacitor. Because if you remember, capacitors and inductors, they don't actually take power, they send power back to they like play with power and then throw it back.
Okay.
For lack of a better, I don't know, that's how it was described to me, it sounded pretty good. And then PF is, goes down the side. Yeah, PF is the power factor. So now I can erase this and work in the space that it leaves. Okay, so 15. Two loads are connected in parallel to a 120 volt source. The first load dissipates 5 kilowatts and absorbs 5 kVAR VAR. Lagging, the second load dissipates 10 kilowatts and absorbs 10 kVAR. Leading, the impedance seen by the 120 volt source is most nearly what? So, this is a job for, yeah. Well, yes, we're going to use math.
Power triangles.
Okay, so this one Jeremy's gonna actually come up and do.
Phasers.
But first, I'm gonna do it, and I'm gonna use
Power triangles.
power triangles, and Jeremy's gonna use phasers, because Jeremy likes phasers and I like power triangles. Because if by the time we're done with this, you guys all remember power triangles, you don't need to know anything else. You're just like power, get some triangles out here. But Jeremy does like his phasers, so. Because that's what we learned in class, in circuits, is we learned phasers for this. So, and the book does it in phasers. Just... Anyway, so I have... So, in this one, I have 3 power triangles, and I use A, B, and T. And I'm not going to draw them, because how many triangles before you get tired of them? Really? And so, the subscripts are A, B, and T. At least 3 more. Alright, here we go. And my triangles are never straight, so now they are. So we have total power, because this is total. This is the first one, this is the second, or first, second, total. So we know that the first one plus the second one is equal to the total based on conservation of power. So we know that PA plus PB equals PT, and we know that QA plus QB equals QT, and I'm going to say QD a lot, so, you know, that's fun. So we have 5 plus 10, and these are both Ks, I believe, yeah, equals what? 15. Absolutely.
Okay.
5, and this one is
Negative.
exactly. It's negative 10. Why is it negative?
It's leading.
It's leading.
So the thing is
That's
early.
the opposite of the last one.
Yep. Yep. Exactly. You're so smart. You guys are great. Yep. So now we have some numbers to play with.
15K.
So
Yeah, the first
thank you. I would have pretended it was 15K even though it wasn't written down. So now we have P, we have Q, QT in fact, and and so what we're going to do is PT squared plus QT squared equals ST squared. Because if you remember from the triangle, this is very obviously a right triangle. Yes. And so you know that P squared times Q squared equals the square root of S squared. No, square root of S. No, S squared. I'm just going to, yes. Okay, cool. So now we are looking for S. So we are going to do this math, and I did it in my head because it's fun, and that's because this is 15, which is 225. And this is 5, which is 25, equals the square root of 250, equals 5 square root of 10. Head math, right guys? Nobody ever does it, but it exists.
It does.
Yeah, and that's ST, which is like the street. So, now we're looking for, what are we originally looking for? We're looking for, we are looking for the impedance. So, then we
What is
do,
the triangle not straight?
So like street.
oh yeah, so the problem with this is that all the problem's answers are in phasers. So at the end I'm going to have to convert to a phasor. That's why he likes to do phasers. But, so anyway, we did. I'm doing all the triangles first, and then I'm converting my final answer into a phasor. So this is the magnitude of our phasor, except it's kind of the magnitude of our, it's the magnitude of our power phasor. So after that, we're then going to find, we have cosine of theta, which is the power factor, equals 15k, which is p, over 5 radical 10. Okay. With me still, guys? So then we have cosine of theta is equal to, I don't know, I just did all the math and got theta is equal to negative 18.4 degrees. Because our problem wants it in degrees. And the minus is from the q, which is negative. Got it?
Yeah.
Okay, just make sure. Out of the way. So the negative is from the q, and I mean the math obviously doesn't say negative, but anyway, the next step is now we need the rest of the phasor. Now that we know the angle, we need the magnitude. So we take our handy dandy formula, which is P equals V squared over Z. You guys remember this one from power? Except this is R, but I used Z because it's Z in the problem, because it's impedance. So this is, I use S, yes. And then so you get Z.
Phasor is S angle negative 18.4.
Yeah. So Z equals 120 squared over 15.8 K. Because this is 5 radical 10, right? Yeah.
Yes.
So then this is 0.911 ohm, well, yeah, ohms, angle negative 18.4 degrees. It is ohms.
Yeah, impedance of those.
I know, but I don't like phasors. This is why I don't like phasors. It just looks wrong to me.
If you want, you can put the ohm after.
What I can do is look at the problem and go, oh, that's how they do it. Okay. So with that, do you want me to erase this stuff for you or some more? Yeah. Okay. Can you do it over there?
Undo it on the
Or-
board over there. We can
Can
erase
you do it
that
right here?
now.
If I erase this stuff?
I was gonna say, does anyone still need the left side? Because we can just erase that.
Okay. Left side.
I'll look
Normal.
at the video.
Okay. Yeah, you missed like all this problem.
Yeah.
Okay. I'll leave the problem up there unless you
Alright.
really need a lot of space, Jeremy. I don't think you do. I think you need about as much space as I did.
All of the space.
All the space, off to you.
All the space. Is it?
Oh, no, that's not it. I put it over here.
This is still like. Yeah, I'm gonna want to reference these just in case. But all right, so we're just gonna do the same problem, but now we're gonna do it using phasors. So again, we have A and B. So we know that for A, the real power is the 5 kilowatts, and the reactive power is 5 K var, because they use var. So basically the same thing, but reactive power. Then for B, oh, and this is lagging, because we get that from the problem. Then for B, we've got 10 kilowatts for the real power, and then 10 K bar for the reactive power. And this one is leading. So to solve for the impedance, we're going to do Z1 and Z2 and then combine them. So impedance of the first part, we need to take into account the 120 volts from the source. And that's going to be squared. And then you divide that by the magnitude. So to find the magnitude of power, what we would do is we would take the square root of the real portion squared and of that added with the square root of the reactive portion squared. So we're just gonna do 5k squared plus 5k squared. So that's not too difficult, luckily. So that's gonna be equal to the voltage over S1. So then we can utilize, and again, S1 is just equal to the square root of the reactive power and added to the real power. So then we can multiply all this out. This should be there. I am going to take up a lot of room, so I am going to erase this.
Goodbye, problem 14. It's nice knowing you.
So then, for Z1, it comes out to be 2.036 according to when you plug that in. And then who remembers how to find the angle portion? Yes. So for the angle, we need to do the inverse tangent. And then is it real over, does anyone know if it's real over reactive or reactive over real? I mean, in this case, it doesn't really matter. Yes. So,
Can I interrupt, Jeremy?
yes.
If you forgot that, you can always go back to the power triangle and look at it and see where the angle is, and then notice that opposite is reactive and real is adjacent. So then it's opposite over adjacent.
That's how I.
Yeah. And then we know that that one was lagging, so that'll influence your sign. So Z1, let's see if I did it all the way out. I did the angles last, so, but I believe that's 45, yeah. So 45 degrees, and then 2.036. And then we need Z2. So we're gonna do the same process, and we're gonna do the voltage over the impedance portion, or the magnitude of the power. So that's the 10k squared plus 10k squared. And then that's gonna come out to half of the other one. So 1.018, and then again we need to do the tangent inverse portion. So 1.018, and then the angle is tangent inverse of 10k over 10k. So again, it's going to be 45 degrees, but the difference is this one is leading. Yes. So this one will be negative 45. So then for the answer, we have two impedances and they are in parallel. So what we can do is multiply Z1 and Z2 and divide that by the addition of Z1 plus Z2. Now, where this becomes a little bit more tricky is adding phasors. I'll erase this stuff. Hopefully did you guys all get that?
It's pretty important stuff, so if you don't have it down by now,
Yeah.
you should get it down.
If not, you can get it from the video, so,
Yes, you can do that too.
because we will be posting it.
Yeah, we will. Although, is there a
Or
limit
reference
to?
it, good call.
Yeah.
So for this portion, we just multiply the top two, so that's pretty easy. You got your 0.36, and then your 1.018, and then you have your, who remembers what to do when multiplying phasors together with the angles? How do you add them? So what is 45 degrees?
Can I point out something?
Yes.
So the Z1
the magnitude is actually not, the magnitude won't have an angle part. So if you have a
Yes.
magnitude of z1, then you don't have the angle.
Right.
So writing magnitude of z1 and having the magnitude and the angle there is incorrect.
Yeah. So the angle, right, yeah.
So-
the magnitude is just this portion, you're right.
Yeah.
And
so
same thing with down here.
Remove the lines.
Yeah. So,
Because the bottom formula, if you did the magnitude, it would just be the magnitudes that you're multiplying, which is incorrect. You have to
right,
account for the angles.
yes. So again, thank you. But yeah, so then you're gonna need to add these. So you have 45 degrees plus a negative 45 degrees. Now, again, adding phasors is a little bit tricky, so it's easiest just to convert it into rectangular form and then convert it back. So that's a fun process. Rectangular is the form where you have like your
IJs,
yeah,
or actually it's
Just-
constant plus I, but yeah.
yeah. So you have like your real portion and then plus something J.
This is what would be like 5k plus 5k
For well, we need it for this portion
Okay.
and this portion. So if you wanted to, it's really easy just to do the magnitude between both of these for that portion, but then the angle portion is still a little bit tricky. But if you wanted to just get the real portion right away, you could do 2.036 squared plus the 1.018 squared, and then that will actually get you this portion, but then you still need the angle portion. So to get the angle portion is the tricky part, and that's why you need to convert it back into rectangular form. Let's see if I can probably squeeze it in down here. So to convert back to rectangular form, did I finish writing that out? No, I did not. Never mind. Okay. Wait. So then for right here though, I'll just write the whole thing out. I mean, it's kind of obvious, but just so you have all the steps. This is the 2.036 and an angle of 45 degrees, and then plus the 1.018 angle of negative 45 degrees. So does anyone remember how to convert that back into rectangular?
What?
Magnitude times the.
Have the like the cosine and sine,
Mm-hmm.
and you add the cosines together, and you add.
Yes. So, do you want to come draw it out? I'm making it interactive.
Okay. All right, let's see. So we have the like the magnitude. I'll draw a triangle again. Oh, it's 45 degrees, but whatever. So you have magnitude, and you have two triangles, and you're adding the triangles together essentially. But I don't know how to draw adding the triangles. But anyway, so you're getting the cosine of the 45 here times so like the square root of 2. So 2, right? I'm doing this right. 0, 3, 6, root 2, and then plus, and then yeah, that would be the same for the cosine. So 0, root 2, and then the other one is going to be minus because it's negative. J, I, and J.
Mm-hmm.
And then you can, those numbers you add up, and you have to find the angle by doing the arc tan of the J part
Yeah,
over the I part, whatever,
yeah,
when you figure that out.
yes.
This is I, J. There.
Sweet. Does anyone want to plug that in? Because like I said, I didn't actually, I mean, it should come out to the same answer that Jordan got over there. But you can plug it in to verify. Good job, Tim.
For this problem, it's definitely.
Yes. That's why he really likes the power triangles.
I can't stress enough how much more I like power triangles than phasors.
Yeah, there was another one where it gave us an angle, and they did a bunch of work with the angles, and we did
Power triangles, and it took like 3 steps.
Yeah,
It was so
a lot
fast.
faster. That was the one with the 3 triangles. It wanted us to use phasors for that one, and we used the power triangles. But since we learned this method, I thought it would be good just to review it, kind of go over
In
it.
case you want to use what we actually learned in class rather than whatever I found out just
Yeah.
over the past week. Are we on the next problem?
Unless, I think Jonathan might be verifying it,
Sweet.
but yeah. And then also you can use phasors on the next problem. It's a little bit, I mean, you don't really need to, again.
Did we do that? I didn't.
If I'm thinking of the right problem, let's see, which one's
16?
that? 16?
Yeah, that's.
Yeah.
Yeah, I think so. There's
Yeah, I did it on mine, yeah.
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 But you decided not to talk about that one unless somebody.
Right, unless someone asks for it. But yeah,
Uh-huh.
so you get the same thing, I'll just write it again, just for the
Okay.
sake of writing it.
Completion.
But that is equal to 0.91,
0.911.
and then an angle of negative 18.4.
4.
Cool.
Okay. Moving on to 16. And 16 we did do in phasors, but if you want to see that, you can talk to Jeremy, and he will show it to you. But for now, we're just going to do, because he did it that way, just to be complete. But I'm going to show you power triangles where we pull out another 3 power triangles. So, for a balanced 240 volt AC 3-phase system, load amps equals 12 kilowatts. Did I say 3-phase?
That's it.
It says 3-phase. Okay, so for a 3-phase system, load A equals 12 kilowatts at a 0.7 lagging power factor, and load B equals 18 kilowatts at 0.8 leading power factor. What are the total real and reactive powers delivered to the load by the sources? And if you remember from the previous, I'm going to go a little bit faster because it's late. It's late. So, if you remember from the first problem, it's a 3-phase. So what does that mean? That means IL equals radical 3I and VL equals radical 3V. And if we were using currents and voltages, which you could, I suppose, but we're not because that would be kind of strange. So since we're not, we don't actually need this, but I just want to refresh your memory so that if this 3-phase ever comes up, you remember it's radical 3. Okay?
I wasn't here for the first problem, so I mean, I know it's gonna go.
You got it. You got it.
Whatever. Is that all you need to?
That was the importance,
That
yes.
was the important thing. That's why I said it one more time. Okay. So, which is why I've repeated the power triangles every time because it's important. We're doing it again, power triangles. You have 1, 2, 3. Well, I'm not going to draw them out this time. It's A, B, T again, so you guys remember the drill. A is 12. This is PA. PB equals 18. and PFB equals 0.8, 0.7. Okay, so the first thing we do is we take the S equals P over PF. So you do the first one and you get SA equals 12K over 0.7. Okay, and you get SA equals 17.74. Correct? I heard somebody saying that. 1.4. I can't read. And then SB, doing the same thing, equals 22.5. I've done the calculation often enough, you don't need it again. So then using P plus Q equals S, and all of those are squared, we know that QA equals 12.24, QB equals 13.5 kilobar. Anybody know why V is negative?
Because it's leading.
Got it, because it's leading. Yes. Yes, so QB is negative because it's leading. So now we do if you guys remember, the total power is equal to this is just kinematics, X and Y combined, if you remember. So PA plus PB equals P total, which is 30, right? 12K plus 18K equals 30K, rocket science, right? And QT equals negative 1.26. And if you look at the answers, it gives you those as the answers. Pretty straightforward, no? Anybody confused by this problem since I skipped, not a lot of steps, but I skipped some of the ones that we did in the past? Any questions? Good? All right, so the next thing we do is we're now going to go to 17, which is not on the board. So I'm just going to have to talk it out because we don't have time to write them down.
This stuff is important.
This stuff is important, but that's actually that stuff wasn't important. Okay, so I need the book for 17. Problem 17. The flux that links the primary and secondary coils of a transformer vary according to V equals V of T equals 5 milliweber sine 377T. Okay, so that's the flux. The secondary coil, N2, equals 500. That's 500 turns, so we have turns. Okay, so what is most nearly the voltage on the second coil? The first thing we do is we go through Maxwell's equations and Faraday's law, which you guys literally just learned about in power electronics. Actually, just learned about being like a week ago, because that's when I wrote this down. We just learned it. V2 equals N2 times the derivative of the flux. The difference between this and the one in the formula that we know is the number of turns, which is actually the turn ratio. I believe that we're assuming that the turns ratio on the first coil is just 1. If there's just one turn on it, So it's just n2, so it'd be n2 over 1. So based on this formula, it's pretty easy. We take the derivative of this. Yes.
So if you weren't assuming that it was 1, if say if it was like 5 or something, then it would be n2 over 5?
It'd be n2 over n1, which would be 5. Yeah.
Okay,
hmm
just checking.
But in this one, we are, since it's not listed, we kind of have to assume it's 1. And the problem doesn't even mention it, so again, we're assuming it's 1. Okay, so we take the derivative of this, which is, this is a constant, so what happens to a constant derivative? You guys know, it just gets to the outside, because it's multiplied. Yeah. And then you take the derivative of this, which is cosine, I believe. That's what we're doing. Yes. Okay, so what happens to the 377 when you take the derivative though? I said this is cosine, right? Cosine 377t. And then what happens to the 377? It comes out 2, right? You guys remember this?
Yeah.
Simple math that sometimes you forget. So this comes over this way, and we multiply all these together, and we get 940. That's what we get. Because this is 25 times 10 to the minus 3 times 10 to the minus 2 times 3 times 377. 377 times 25 is 9,400. And then times this is times 10 to the negative 1, which cancels 1 out. And I'm pretty much just going off the book, so I'm guessing kind of. Everybody still following? Any questions? Comments, concerns? Got a different answer? Okay. I'm right? Oh, okay. If you finish it and come back to it later and say, oh look, we can talk about it, I'm gonna leave it on the board. So now we are on problem 18. Except we're not on 18 because, fun fact, we don't know how to do 18. So 18 is about it's about RPMs, and it's just bizarre. We think the book's actually wrong on this one because we get a different answer and the numbers don't make sense, and it's very simple.
Per minute.
Per minute. Yeah.
But it starts off with revolutions per second, and then we convert it.
And
And
they
then-
use 120 to convert it, and we think they're wrong. So. Moral of the story is we're not doing 18. Problem.
'Cause if-
This is 17.
Yeah. We don't want to be wrong and then like teach you guys wrong.
Yeah.
So
Yeah, and we don't want to say that the book's wrong because we're not that certain, I guess. They could be right and do something that we're not sure about, so we're just gonna not talk about it and pretend it's not gonna be on the test. Okay, so the next question, problem 19. A manufacturing plant operates with a large number of induction motors. As a result, the plant has a low power factor and is charged for more power. Cost can be reduced by dramatically increasing the plant's operating voltage. Increasing the plant's resistive load. Adding lagging reactive load. And adding leading reactive load. Yeah, it's a multiple choice question. So, any ideas?
You want to decrease Q.
Which key? Well, I mean, I drew my things where this actually should be like this.
You want to add negative Q.
Why?
So if it's a power triangle, if the power factor is very small, it's because compared to the real portion, there's a lot of reactive power. There's a lot of Q compared to P. So you want to increase your P to Q ratio, and you can do that by adding negative Q.
Close. So lagging is positive, right? And leading is negative. And you said leading, right?
You want to add the negative one.
Which is leading. And you know leading is negative because you guys remember that, right? You don't remember it just because I wrote it down here. So anyway, and because we did it over there, if you remember the induction, the inductors are the positive, and based on the sign convention that I've had in the past, the inductor Q is positive, and Q from capacitor is negative. So I'm assuming that that's the right convention, but if it's not, then it's the convention we've used, which, I mean, if you do it the other way around, you get the right answer anyway. So Q from a capacitor is negative. So in this case, we have an inductive source, so we need the negative version, which is makes him right. But that's just a more complete explanation. Just expanding on a couple more things. So that was problem 19. I'll leave that up there too. Problem. Yes. Did we do problem? Oh, yes. And then problem 20 through 23 are electromagnetics, which we're learning right now. So if you've forgotten that, you're sunk. Yeah. Also, there's the possibility. Wait. Dang it. I'm sorry, guys. Did anybody need this? I can write it up again if you needed it. You needed it? Okay. I can put it back if I remember where it is. Okay, here it is. Okay, there it is. Let's erase this stuff. Because nobody needs phasers.
Hey.
Hecklers from the back. Say, hey.
Phaser game.
All right. So now we're in the exciting class of control systems. Control systems. We're on problem 24. An open loop function fs is given by k over s times s plus 1 over ns plus 4. Find the poles. No, we're skipping electromagnetics. We're in control systems, which you might have actually forgotten.
0, -1, or -4?
0, -1, and -4. You just take the bottom and you factor it, which it's already done. So you set every part to 0, and then you get 0, -1, -4. I'm not going to actually do the math on that one because it's really easy math.
So
So,
I need you to do the math.
well then you can go take.
Can you draw the triangles for that problem?
No, I can't. It's control systems. What I can do is draw you this.
Draw triangles for
That's a rectangle.
He like draws that.
This is the block diagram.
It's the controls rectangle. The other one was the power triangle. This is a controls
Okay.
rectangle.
Yeah, this is the controls rectangle.
Do we
So-
have circle?
Hmm?
Circuit circle.
You get the circle. You get the circuit's loop.
Actually, I like circuit circle because that's what Chun. This is important. That was important.
All right.
So I guess that's technically more a spiral.
All right, but we are now at an hour and a half. So, is the battery still working on that thing?
We lost power momentarily because it told me battery is low and shut off. So, but that was a while
Did
ago.
I miss it? Did I-
That was when you were rushing through this problem on the right. So, I mean, you skipped steps and then we lost power and then we got power back and then you were done. So, well,
So that thing just skipped all the steps, but you got to get a shot of it, right?
yeah.
Okay,
We got
so
it. We got it on camera. So if they have
need it,
questions,
they can look at it. Oh, it's still up there. So
Yeah,
it's
yeah.
good. Okay, cool. We're good.
I said if they have
Okay.
questions on it, we can explain. But
Yeah, but we didn't have questions on it because it was all.
well, no, if anyone on the video does,
Oh,
because they won't get as much of it as we got, and we still got a speed version of
And
it.
we got the speed version. You are absolutely right. What problem am I on now?
Well, they should have come to the session.
20.
past
Wait,
True. True.
This is 24. Yeah, we're on 25. Okay, cool.
Problem number plus
25. 25. For the control system shown, E of the error function, whatever it is, it's epsilon p for some reason, equals the limit as s goes to 0. Luckily this is given, otherwise you guys would be struggling to rack your brains on where this law came from. 1 over 1 plus g of s, which actually is a formula given, if you remember. But you don't need to because it's given. So then now we have the actual control system, which is R, and I'm not going to put the S because I'm lazy. This is summation. And here's the controls rectangle for you. You got 10 over S plus 2, S plus 5, and all of that is in a feedback loop. And this is C for some odd reason. Okay. Okay, so we're looking for the value of the error coefficient, which is really easy because you just take this and you plug it in here. So G of S, if you guys remember, is the open loop circuit, the open loop
Transfer function.
transfer function, open loop transfer function. So the open loop is just this right there, that way, without the feedback. So it's 10 times 10 over S plus 2, S plus 5. And in case you guys are worried I'm going off my rails, Jeremy can't help me. So, it's because he did not do this with me, because he's a slacker.
Slackers.
That or I had class or something. But
I did it while you were getting dinner.
Also,
yeah, as you noticed, I had to eat it here.
Uh-huh,
chick is like,
uh-huh.
Just saying.
Okay, so how long were you in line? I actually stopped by your apartment and they were like, oh, he went to get dinner.
Yeah.
Okay, so that's the easy part. So then now we can plug the rest of it in. And you get 1 over, did I do this? I did this wrong. No, I didn't. Okay, I did it right. I'm just going crazy. Okay, so 1 plus 100 over S plus 2. I need to write it. S plus 5. All right, so we have this, and we have limits. S goes to 0. Okay, anybody confused so far? Good, everybody looks busy. 1 over 1 plus 100 over 0 plus 2, 0 plus 5. So then we get 1 over, I just did the limit, which you guys remember from pre-calculus, and 182 I think also covered this.
and pretty much every
2 times 5, and pretty much every math class after that. So this is 1 over, that's wrong, I can't. 1 over 1 plus 100 over 2 times 5 equals 1 over 1 plus 10 equals 1 over 11, which coincidentally is the error coefficients. Anybody lost?
Isn't that what it's supposed to be?
What it's supposed to be asking?
Yeah.
Yeah.
You said coincidentally, like, that's what we're.
Victory is ours! Victory is ours! Alright.
I was confused for a second.
Okay, so you have an error function, which is based on the feedback and the. So if you remember, if you remember, when you plug in,
I didn't take the class.
you didn't take the
I
class.
didn't take the class.
Okay, so you don't remember, so I'm going to go over this, and I'm amazed that I remember
Is that about
this.
control systems?
So yeah,
Aren't you in it with me?
No.
Oh, I thought you were.
Okay, so first Stephen. So what you have is you have a function, right? You have a function r. So let's say function r looks like this, right? Okay, so function r looks like this. Function g of s, which is this portion here, which is this open loop function. So it's the 10 times this. Everything in a straight line is open loop. So you have that. So what you do is you take that, and then that is going to change this function, right? So this function is going to be multiplied by the g of s to create this, except you have the feedback. So the feedback is going to come over here, come through here. You take LabVIEW?
Yes.
Yeah, okay, so you remember feedback from LabVIEW.
A little bit.
Okay, so you take the feedback, a little bit, because it was what, 2 years ago? So you take the feedback over here, and then the feedback is going to come in here, and the long story short is the error signal is this signal right here. Because what it is it's minus here and this is plus. So what it is it's going to take the system's going to take the actual value and subtract what you got to come up with the error signal, and then it's going to do that to create the system. So long story short is, I believe, if I remember right, the error coefficient is the amount of error you're going to get when the system's at steady state. So if our coefficient is 111, so if the value at a certain time in steady state is like 5, the value of the actual, what we get on the outside, is going to be 5 times 1 over, except that's not right. It'd be what's it called? Yeah, except it'd be bigger, I think. So it'd be 5 plus 5 times 1 over 11, I believe is what it is. So then it'd be 5 plus 0.5? You guys can do the math if you want to. But then it comes out something like this. So that's what the error coefficient is. And then, yeah. Jeremy, that sound right to you? Does that seem right to you?
Sure.
Okay, John thinks it's right. He took controls.
Sounds
Tim, you didn't take
familiar. It's just I haven't done
controls. I mean,
controls.
you've done this. This is the third
Yeah.
homework assignment.
So, but what's given, that's the limit part's given, right? And the,
Yeah, the error
the
function
whole
is given,
diagram's given.
and the diagram is given.
So that- yeah,
Yep.
that's-
All this I did.
yeah, just
Okay.
making sure.
Yep.
Yeah, that's, if I grab that stuff, we're good.
Yeah. Okay. That is that problem. Now we are on 27.
The feedback loops.
27. Jeremy, did you ever come up with it? You did, and we said no. We noped out of that one. So we are
Yes.
on 28.
It can like adjust itself.
So nobody needs this stuff anymore, right? Brian, you need this stuff here? Okay. Oh, Jeremy, did you notice the camera shaking? Because I kind of did. I
Yeah,
wasn't sure if it's from the table. Maybe.
I think it's just the lens adjustments. I'm not sure.
Okay. I don't know. If we could not in the future have that, that's cool. But I mean, it's not a big deal. I'm not gonna watch these.
Well, I don't know what's causing it. It's just,
Okay, so we noped out at 27. So we are on 28.
I didn't tighten the tilt lock, but that just prevents us from.
No, it's fine. You don't need to fix it today. It's not a problem. For a control system whose open loop gain is G of S, remember G of S is the open loop gain, always and forever, equals 20 over S plus 10 to the third. This one problem is really easy. Okay, so for open loop given there, what is the approximate break frequency in hertz? No, in hertz. What is the approximate break frequency given a pole? Anybody? Transfer functions. Circuits. Remember, you have a filter. In this case, it's a low-pass filter. No? Nobody?
Something to do with 10 to the third.
Exactly.
over-
Break frequency is the pole. So if you have a function with pole 1, pole 2, pole 3, your thing is gonna look like
That's
this is circuits.
that's
Yeah.
an omega. Or
Huh.
radians per second, right?
Yeah. So if you have this is pole 1 is maybe here, pole 2 is here, pole 3 is here. It's gonna go like this. Whoa, I can't draw. It's gonna go. Thanks. For the confidence. It's gonna go like this. You guys remember this? And then it's gonna go even steeper because it's the third pole. So you guys remember this. So if we just have one pole, it's gonna stop at that. It's very simple. There's just one breakpoint. So which is 10 to the 3. Except like Tim said, it's in radians per second. Right? So we need to convert that into frequency in hertz. That's the problem. What do we do? F equals omega over 2 pi equals 1000 over 2 pi equals approximately, I didn't do the math on this, so I'm just taking the book's word for it.
18 or something?
180,
Yeah, or, yeah.
160.
Yeah, I was gonna say it's 160.
Mm-hmm. It's 159.2 is what the book says. But they like 160 because it's on the multiple choice. So that's problem 28. Any questions on 28? Cool. Pretty simple. Because then you just have to remember what a low pass filter is, or a high pass, or
Or what a
the,
transfer
the
function
concept
is.
of a pole. Yeah, or what a transfer function is. I need to keep this.
Yeah. So you have one.
So if there's multiple poles, are there just multiple break frequencies?
Yeah.
Okay.
Yes, and you when you have multiples, you go with the first one, I believe, right? Don't you go with the first one? I think you do. But
You mean multiple? Oh wait, I see.
it's a play on
What
words.
if you have
If you have multi-poles,
yeah, zeros don't have break frequencies, do they?
they do. But
okay, is this called
you're
the same
talking.
thing then?
You're talking. Yeah. Generally, they have if they have like if they have more than one, they're probably going to give you one that looks like this. Yeah, probably. In theory,
Yeah.
if they're nice. Like if you want like looks like this, well, you'll have two. But and the FE exam really is not mean to you. It just makes sure that you understand the concepts, so you get easy problems like this. So, and plus it's multiple choice. How can they give you more than one? Yeah, it's like, come on. If you do one wrong, if you do one right, you'll get all of them from that one. So, not a big deal. This is the wrong order. Now we are on 29. 29. Oh, we moved into communications. That's why it's hard. That's why it got hard. Okay. 29. Now we're in the communications section. Does anybody need this? Before I go wantonly erasing it, like I did over here. Any problems over here? 3 more, including 29. They're quick. Okay, so if you guys, since you didn't know this, from 24 on, I did in 15 minutes. I did right before this meeting in like 15 minutes. So, so they're easy and they're fast. So 29 is if you have a impulse function. Don't even. It's an impulse function. Just trust me. It's not backwards.
Oh yeah, no, that's right.
It's many things. There's many things wrong with it, but it's not backwards. This is a variable called a,
Yes.
and this is the impulse function.
You lost me there.
Impulse function. It looks like this.
It's a lowercase delta. Is what
Oh,
it's
it's
letter.
delta, okay.
Uh-huh.
Yes, backwards.
It's not backwards. I'm reading.
That's what I said, but I think it's not actually. No, it is.
I'm
I
reading
think it would look more
I'm-
like a D, but it,
It doesn't. Okay, so anyway, so this is the impulse function, and it's actually at 0. So, yeah.
The derivative of the set function.
Yes. So, we're looking for the Fourier transform of of this. The Fourier transform of this, which you can remember.
I love Fourier transforms.
Yeah, you do. They use this formula, xf equals. Where's my
This one I feel like would be in the chart, like, you just need to check.
Yeah, I'm 100% sure it is. Because charts always include the impulse function.
Yeah.
So you can check the chart, but just for fun, I thought I'd show you this formula.
Is it
2 pi,
You can
which would
erase.
be omega, because it's f.
Yeah.
Yeah.
J omega t.
And then it's, you don't need to know it's z.
Phaser gang.
dt. So that is the formula for this, which you really can't plug the impulse function into it, but you know, if you could. The formula comes out, and the answer is the Fourier transform of this function is just a. It's just a. So very easy, very quick, conceptual, lots of fun. So, do we need this anymore? As we march across the screen, anybody need this? Going once, going twice, gone. Pretty important, so make sure you write it down.
Unless you do the triangle way.
Unless, that's right. Who needs phasers anyway? Okay, so the Fourier transform of a discrete time signal is it's a periodic function. So we have a discrete time. So we have something like z of, what is a discrete time function represented like?
Sum of stuff.
I don't know, whatever. You guys know what a discrete time function is. This one's conceptual. So you have a discrete time function. Is the Fourier transform a periodic function? Is it non-periodic analog? Is it non-periodic digital? Or finally, and most important, is it periodic if f of z? Sorry, my writing's bad.
Is it
because it's
just
not numbers.
periodic?
Is it just periodic? Anybody?
I don't remember.
Anybody else? What is a Fourier function? What is, by definition, a Fourier function?
You're like adding up a bunch of sines and cosines.
And sines and cosines are,
Periodic.
so the function must be periodic.
But if it's, I'm pretty sure if it's not discrete, then it's not periodic.
You're wrong. Wait, probably. No. If it's, let's say it's
Well,
if it's not discrete, then it's maybe a square wave. What is a square wave? Is square wave periodic in Fourier? Yes.
yeah.
Yes, it is. Yes. The answer is yes.
But is it, if we're transformer, if we're Fourier series?
Fourier transform.
Okay.
Transform. Which means it's always periodic, because it's a sum of sines and cosines, which by definition are periodic. So the function must be periodic.
Yeah,
Still confused?
maybe a little.
Maybe a little. Well, you can always Google Fourier transform, but because Fourier transform is an infinite sum,
Just because I remember learning that some of them were not periodic.
of sines, yeah, sure, plus plus
The
cosines.
sines and cosines cancel.
Well, obviously, if your signal was, let's say your signal was a square wave and stopped, then as you got into the farther ends, they would cancel. Because at this point it has to be 0, and at that point it has to be 0, and it has to keep being 0. So obviously after this point they would cancel out, so you'd just be left with the ones right here, which would be periodic. Make sense?
Just go.
Just go with it? Okay.
I mean,
If it doesn't, I mean, if my explanation isn't good enough, you can always talk to somebody who knows more about Fourier transforms, which is pretty much everybody, so. So there's that. Okay, 31, which is the final problem we do, because we don't want to do 32, because it's long and hard, and I didn't know how to do it. Probably because it's communications. Which I didn't realize we jumped sections, but that's okay. In an AM signal, a 900 kilohertz carrier is modulated by what does modulated mean? Anybody modulated?
it's the radio.
It's got something that it's basically like it's messing with it. Yeah. Yes. It's modulated by a music signal that has frequency components from 1 kilohertz to 10 kilohertz. So it doesn't look like subtraction. I'll put it over here. Now it looks less like subtraction, right? Just say yes. Yes. Okay, so the range of the frequencies generated for the upper side bands is, and then it gives us a bunch of ranges. So, based on this information, we're looking for the range of the frequency. Anybody? It's really simple. So we have, let's try it out. So we have our function. This is 900 kilohertz. And then we have 1 kilohertz to 10 kilohertz, and I just realized my drawing's actually going to be backwards because reasons. But anyway, so this is my wonderful drawings. Basically, what you do is you add them together to generate your range. So it's just 901 to 910 is your total range, which kind of makes sense if you think about it. It's going from, when it's modulated, it's changing it a little bit. So anyway, I didn't totally understand it, but it's just 90 plus 1, 90 plus 10, so it's pretty easy. So I figured I'd include it for fun, because it's easy. So yeah, you don't want these anyway. So with that, that's it for the problems. Are there any questions on any of them?
Can you go for the triangles?
I can. Would you like me to?
If you want.
Okay. I've gone over them enough, I think. Any other questions? If you have questions later, you can always ask me, or you can look at the video and see if that helps. And with that, we have, what, almost an hour and 45 minutes of film. So, hour and 40 minutes of film. So, I was going to say something, and then now I can't remember.
Good job.
Yes. Well done. Way to go, guys. Way to stick through this 2-hour thing. Oh, yes, here's what I was going to say. So, if you didn't catch it, the first thing we went through was power. The second thing we went through was control systems. And then the third thing we went through was communications. So, if you're looking for control systems, communications, and power, this is the video to look at.